you for inviting us to this class. Very pleased to be here. So, actually, I should correct one thing. I actually don't have a PhD, so I'm not a doctor. So, but I've been doing this an awful long time. So, what I'm actually going to be talking about is the system-level model-based design using a relatively new product that we've been developing called Maple Sim. So first of all, can I just find out how many people are using Maple? Okay, so, so we have a few people using Maple. How many haven't even heard of Maple? Okay, that's good to hear. Actually, very glad to hear. So what I'm going to do is spend a little bit of time just introducing you to the company MapleSoft, and then talk a little bit about Maple, and then go into the Maple Sim in some depth, and then show you how you use Maple with Maple Sim. So the company's been around, the technology has been around for about 30 years. It came out of the University of Waterloo in Ontario. If anybody doesn't know where Waterloo is in Ontario, they're the people who make the BlackBerry. They are based in Waterloo. In fact, the founders of Research in Motion, or RIM, actually came from the University of Waterloo, and the whole town has exploded because of that. We made a small contribution to the employment in the area. The company was founded in 1988, and we developed this technology called symbolic computation. And just so you understand what symbolic computation is, the research group wanted that the computer science faculty at the University of Waterloo wanted to come up with a way of getting a computer to do mathematics. This isn't throwing a problem or numeric solvers at a problem. This is to do mathematics in the way that you do mathematics by hand, spending many hours, many days doing this, getting things wrong, and then but manipulating the equations and combining them together, and then deriving a solution. So that's the fundamental part of our technology, and then on top of that, we provide a wide range of numeric solvers to be able to take the equations that you derive, or the systems that you provide, and then solve them numerically. And consequently, we become a leading provider of high-performance software for engineering, science, and mathematics applications. The product is called Maple. As of today, we're at Maple 16. We launched Maple 16 today, and then in 2009 we became a Japanese company. So we are now part of a group called Cybernet, who are a major engineering services provider primarily for the automotive industry, but they do provide technologies and services to other industries. So as I mentioned, we're based in Ontario. If you have a look on a map, we're between Toronto and Detroit, and so very close for the automotive industry in Michigan. We have offices in the UK, Germany, and France, and around about 30 independent representatives, including my colleague here, Renato, who's our representative in Brazil. And we have about 140 employees, either at our HQ or spread around the world. And we spend around 50% of our revenues on R&D and actually developing these products. So we have a very large R&D department full of very smart people. So, in terms of our engineering solutions, we developed Maple, and then 3 years ago we developed or released Maple Sim. And I'll talk in more detail about that in a moment. And we provide professional services. In fact, my group is the applications engineering group. So we have between 10 and 12 individuals, engineers, with certain specializations that we can offer services to our customers, and including things like being able to develop turnkey So once somebody has developed a solution to a problem, we have tools that are able to deploy that throughout an organisation without adding license costs. So Maple itself is a world leader in numeric and symbolic computation. You can think of it as a tool that gives you access to a lot of power in the solving power of the government. You can think of all the knowledge of all those mathematicians and all those physicists and scientists all bundled up in that kernel. And then we use a graphical user interface to be able to gain access to all that knowledge and to apply solving techniques to many different problems. And we do this in a very easy user interface to allow users to analyze, explore, visualize and solve major problems in mathematics and science, and various other computation problems in a single environment. We should also dwell on the fact that this interface is effectively a technical document. So you can think of this as a live technical document where you're providing information about how you arrived at a certain solution, and illustrations, plots, diagrams, pictures can all be embedded in this document. Well, that means that you can then pass this to colleagues and they can just put in their own data and see the results come out of that system. I should also point out that Maple is actually a programming language. You can use this language to create very sophisticated algorithms and solving techniques, and then, if you like, hide them behind a single function call, or put them in behind a button, or in this case a knob or a slide or something that you want to put into a user interface. So it's a highly flexible tool. And then just an example here of a vibration analysis worksheet that just, you click a few buttons and it does the analysis for you. So this is what I mean by taking all that hard work and being able to deploy it for somebody else to use it. So the main reason why I'm actually in this country is to promote MapleSim. So MapleSim is a physical modeling and simulation platform that uses a graphical user interface, a block diagram interface, to allow you to define multi-domain systems for things like plant modeling, for control design, or just being able to prototype some kind of system that you want to understand the behavior before you start building a prototype of the whole system. Anybody here using Simulink? MATLAB and Simulink? Okay, so totally the wrong audience here. Okay. We use, it's very easy to use schematic diagram to allow you to put these components together. And then we're using the symbolic foundation of Maple to interpret this diagram and turn these into equations. So what you end up with are the equations of motion, or the equations that define the behavior of the system from that diagram. And of course, because it's integrated with Maple, you can leverage the use of Maple, the power of Maple, in terms of doing any kind of analysis on the model inside of Maple. And what we found when we presented this to customers, or customers have started using this, is that the way that they used to do this kind of work would take months. And with a tool like ours, we can reduce this down to a matter of days. So there are sort of three parts to the whole structure of the MapleSim that really is truly revolutionary. One is the fact that we have this system-level capability of being able to bring in components, engineering components, and connect them together and define the system equations from that. Once we have those equations, we can do analysis on those in the Maple environment. And then the third one is the fact that we can actually generate code, C code, from all the results of our analysis and the modeling. We can produce code which is very fast. This is important for a couple of reasons. One is, well, everybody wants faster. Certainly, you start to get into things like systems optimization, where you want to run these simulations tens of thousands of times. You want to be able to run as fast as possible. The other application is if you want to take this system and run it in a real-time environment. You have a very narrow time budget in which to execute your code for your plant model or for your system model in a hardware-in-the-loop or real-time system. So it's critically important that you can get as fast as possible code and maintain the fidelity of the model that you're representing on this real-time system. And we can do this because we have this powerful symbolic capability. So everything comes down to the ability to generate equations for doing this. Since you're not Simulink users, I'll skip the next two slides. I'll certainly talk about a little bit about this one. So, actually, I'll just take a little bit of a step back. So, up until recently, if you wanted to use a simulation tool like Simulink, you would have to take this schematic diagram, manually derive the equations of motion, get them into integral form, and then build what is effectively an analog computer with integrators and gains and loops to be able to solve this, those equations that you've derived. So what you end up with is a representation of the system that looks nothing like the original. So with MapleSim, we can just simply take that schematic and bring it into the computer. So now we can just drop in a mass, spring damper, mass, spring damper that represents those components in here. And then get the behavior of this system. But not only that, using MapleSim capability, we're actually generating the equations of motion from that. So you can actually visualize the equations, which of course gives you a lot more insight into the behavior of the system. Right, I'll skip this one since there are no Simulink users. And actually I'll skip this one as well, since this is just really talking about being able to take the code that we've generated and then target very specific tools that are further down in the tool chain. Sorry? Okay, so that's just a little bit of an introduction to our products, and who we are, and why we are here. So what I'm going to do here is just load up MapleSim and give you a little bit of a demonstration, and I'll show you a little bit of Maple as well. So this is the MapleSim environment. This is a workspace where you're going to build your model. We have a couple of palettes over here that I'll explain later, but one is the settings tab for setting up your simulations, and then we have a plots tab for creating different types of plots. And this is a parameter inspector, which I'll show you a little bit more in a minute. On the left-hand side, we have a series of different domains of components. So we can do electrical components, mechanical. We do 1D rotational and translational, and also if you want to go beyond one dimension, we have multi-body. I'll show you a little bit more of that as well. We can provide hydraulics, thermal modeling, electromagnetic modeling. And we have a couple of specialized add-ons for transmission modeling and vehicle models with tires. So I'm just going to go into my 1D mechanical and put together a simple model. I'll bring an inertia, so this could be a shaft, a rotating shaft, and I'm going to drive it using a torque driver. And then I just simply connect those two things together. So this defines what the relationships are between. If I take a look at the underlying equations, or what is underlying this block, this component, then we can see here, these are the equations that are being implemented when I use that component. So this gives me the speed and torque out of the shaft, and that's actually determined by the behaviour of the inertia and the acceleration. Now if I click on this wire between them and select a probe, here I can see all the properties that are available. So these are all the properties that are being passed backwards and forwards between those two components. So I'm going to select speed and torque. Then run this. So we can see here we've got a static torque being applied. And because there's no resistance to the inertia, then this thing will just speed up to infinity. So let's put a little bit of a load on this. So I'm going to bring in a damper and a rotational ground just to connect it to a fixed ground. And I'll connect this to the other end of this rotation, of this load here. So now I'm going to just put a damping factor in here. And then run the simulation again. Well, way too big. There we go. So now we can see that the damping effect, applying a load to the system as the shaft speeds up, and then it'll come to a balance point at 1 radian per second on here. So just doing this is a very, very quick process to be able to put this type of system together. And here's where the magic happens. If I load up Maple, so this is the Maple environment. I've just loaded we have a series of templates, which are just Maple documents, to help you get started in the analysis process. So just load these equations up. So load the model up, and then that will extract the equations. So here are the states in the system, and these are the parameters that have been extracted from the system. Now the parameters have kind of funny names because they're just machine generated. You can always change these so that they have a meaningful name for you. And here are the equations. So the equations of motion for that system. If I want to, that's a simplified version of it because all the parameters are being substituted with values. So now I'm just going to make all the parameters symbolic. And now we have the equations for that system. So this gives you the first starting point. Obviously, as you create more and more complex systems, then these will start to get much more complex equations. And I'll show you a bit of that in a minute. So, so this is just showing you one sort of kind of mechanical domain. What we're going to do now is just show you the multi-body components. I'm going to throw on. Actually, I'm going to throw on one component. We've actually been touring with a good friend of mine for the last couple of days, and who's a huge Nicholson fan, and he keeps telling me that, and I don't do enough, say enough about this particular block, this one block. He's actually an aeronautic engineer, and he found that with this one block, this replaced something like 27 blocks in Maple, in Simulink, because everything is in here that defines the dynamics, the 60-degree freedom dynamics of, for him, the aircraft. Everything at the center of mass. So not only is it allowing you to provide the mass and inertial data in here, if I go back into Maple, and extract the equations of this, him, this was the magic. So that one component has all 6 degrees of freedom equation of motion in there. So I'm forever in the debt of my friend Sergio for finding this out. So what I want to do with this is to build some kind of linkage. So I'm going to pull on a couple of these components. And these are, we call rigid body frames. They are points of interest between one point and another in 3 dimensions, in X, Y, Z coordinates. So what we're saying here is...
Como tem uma certa comparação com os gráficos de Feynman, você está associando matemática para cada peça. E daí você vai montando, só que aí não é uma reação de partículas, está montando, já que a palavra misturar ciência e inovação, tem que vir com equações e criar esses componentes. E daí você cria para a inovação. Então, a inovação é uma coisa de fundamento matemático.
Something else I've got to put up here is for the multi-body components, you have this visualization tool that allows you to view what you're doing as you're building your component. So these body frames are used to define, in this case I'm just defining the distance between this point and this point to be 1 meter in the x direction. So I've done the same for this, and we can see that appear in here. What I also need to do is just put a fixed frame in here. Now, I'm going to run this. Now, what do you think is going to happen? Anybody like to guess? It's going to fall. Because I haven't actually attached this to anything. And this is one of the beauties of this visualization tool. If you forget to do something, it's very obvious when things go wrong. I'm going to put in here a revolute joint. And so this revolute joint is just a hinge. It's going, the axis is going to the z-axis, so into the screen. And now I'm going to run this. Anybody like to guess? Simple pendulum. Because we actually have gravity, so it's just pulling on gravity. And again, if I go into, actually, I think I already have it up. If I go back into Maple, I extract these equations. So now we have a single state, which is the angle of that revolute joint, and there we have the equation for that pendulum. Make this a little more interesting. Let's copy, paste this. Bring these together. Run this. Oh, that's the thing. So let me just do this again. I'm going to put let's put some probes in here. So now we just have a double pendulum. It's just going to swing somewhat chaotically, and this will just go on forever because there's no friction or damping in here. But again, if we go back into Maple, sorry?
May I make a comment?
Yeah?
Vocês vejam o seguinte, vamos dizer que vocês têm uma teoria qualquer, queiram fazer um pêndulo duplo, então vocês têm as equações, e daí vocês montam aqueles componentes, e daí ele acaba fazendo o desenho para vocês. Assim. Quer dizer, isso é um momento muito grande, muito notável, que está se atingindo essas indústrias de softwares, que vão dizer, todo o sistema de equações aqui, eles têm um significado claro ali, não é uma coisa. Agora, de onde vem essas equações? Vem das teorias que vocês vão estar desenvolvendo. Então, por isso que eu quero que vocês entendam que vocês estão unindo ciência com inovação. A ciência vem a teoria de vocês. Isso aqui vai permitir vocês fazerem esses componentes, etc., criarem inovações.
Just for speed, I'm going to pull up just one I've created, this bit part of the examples. It's the same system as a double pendulum, but this time we've turned these into compound subsystems. So if I double click in here, there's my rigid frames, and there's my rigid body. But this time I have variable names for my mass. So instead of 1 kilogram, I have m for my mass. And this is because I can parameterize all my models. So I can just use symbolic names for my parameters and then have numbers for different values for different instances of that component. So here we got, so the length is 1 meter, and the second one is the length of 3. And we run this. Then we have a lot more chaotic system. And that's going pretty crazy there. So now what I'm going to do is add another constraint to this. I'm going to put a prismatic constraint and a relative joint. Connect these together. This to the ground. So a prismatic joint is just a joint that constrains this point to move along this x-axis. Selecting on the x-axis. So it's constrained to just move along the x-axis. And so if we run this, we now have the start of a slider crank mechanism. Now if we go into maple, little system. Now we're starting to get. Try again. I was expecting to be a much longer set of equations. Let me just try something here. I know why. Create a new model. This. Okay, this is more like it. So these equations are now starting to get a little extensive. Now, if anybody's involved in multi-body mechanics, then you probably do know that there are actually other ways of being able to represent these systems that make it a lot more sense. And we have actually a set of commands that are specific for the multi-body system modeling. And these are a set of commands that are in a Maple library called Maple multi-body. And I'm just going to extract the equations. And now I'm going to build system equations in a more appropriate format. And this tells me that this is a 1-degree freedom system, has 3 generalized coordinates and 2 algebraic constraints. So from this, I can then extract much more information than just the raw equations. So for example, I can find out what the position constraints are.
Sir,
Yes?
question please.
Yeah.
Do people in other areas like biology, medicine, are they also making simulations with these facilities, or it's still people more connected to physics and engineering?
It's mainly physics and engineering. Yeah, I think the only sort of biological applications I can think of are prosthetics types of applications. That doesn't mean to say that it can't be used for those things, but certainly, if you look at the nature of the built-in components, they're really geared towards the sort of engineering kinds of applications. Now, one of the things I'm going to show you now is how I can use Maple to just put equations in and produce my own components. So what I'm going to do here is
Mas vocês podem desenvolver, compreende? Essa é a questão. Quer dizer, a questão é que esses softwares são abertos. Vou dar um exemplo, por exemplo, a Toyota e a Honda usam muito agora. Então, eles desenvolvem situações.
Vão colocar novos sistemas aí. Né?
Então, por exemplo, o que é importante numa conversa geral da gente, o que é ligar ciência com inovação? O que ele fala tanto aqui não é ciência e inovação, o que é ligar isso? Então, a ciência te dá uma lagrangiana. Aí você, com a tua lagrangiana, você constrói essas coisas. Está ligada à tua biologia, ao eletromagnetismo, o que você quiser. E daí você cria suas inovações possíveis. Entendeu? Então é um assunto em aberto, mas digamos, e você pode criar tudo isso aqui sem fazer programação, não precisa fazer programação. Não precisa ser um Maple para fazer isso aí, entende? Assim, então eu acho que essa que é a ideia que eu queria passar para você.
Quer dizer, você não tem que programar, você define o teu sistema, coloca as tuas equações e aí trabalha com as equações que você não precisa programar.
Você monta aqueles que eles chamam de componentes, sem programar. Entendeu? Assim. Então por isso que eu estou falando, você daí, agora eu estou tendo uma ferramenta para unir ciência com inovação. O que é unir ciência com inovação? Qual é a ferramenta? Is a good discussion for us. Qual é a ferramenta? O que é unir ciência com inovação? Então você está com eletromagnetismo não linear. E daí você quer, eu quero fazer agora aparelho, fazer um liquidificador, alguma coisa com eletromagnetismo não linear. É possível, isso aqui é uma ferramenta para você fazer. Senão você só ficaria resolvendo os potenciais, etc., não lineares. Assim. Então esse que é o ponto que a indústria só...
One more question. Do people in economics use that to make simulations of stock market in all situation to connect this area?
I'm aware of one group from the University of Kingston in Jamaica who are actually came to see us, and they're using Maple Center doing this kind of work. Actually, I haven't pursued how they're getting on with that. It's a good question to try and find out. But they wanted to look into, econometrics was the area that they were looking at.
The lab view is inside to Maple Sim.
Lab view?
Is
no. What we have is a way of being able to, once you've built a model, of transporting that to LabVIEW. But a LabVIEW is a very separate product. It's just being able to implement the model in a LabVIEW environment. Are you using LabVIEW?
in the past I used.
Okay. So what I'm going to do here is just talk about, if you have a system that is mathematically defined and you want to implement it in MapleSim, then you can use this custom components template. This particular one, I'm just going to use it to create an electric motor. I apologize for my engineering examples. And here you just simply type in the equations. So we have two differential equations that define the behaviors of the system. You just type them in. The rule when you create these equations is anything that is a function of time is a state.
So, sorry, I can see it's a Lagrangian or what's the equation?
This,
Yeah.
it's
Equations of motion.
the equation of motion for, well, what this is,
But you write, you program a Lagrangian, for example.
yeah, just typing in a second order system, or, yeah, just as, you know, you can put it in a Lagrangian,
Okay.
yeah, absolutely. PDEs, you can put those in as well.
You have your theory, and then you go ahead with your theory, for you can start to Lagrange.
I'll show you a more extensive example of it as well, so you can see anything, any set of equations, you can just type them in. The rule is, the only rules are that anything that is a function of time is the state, so it's whatever is changing, and anything that isn't a function of time is a parameter, so they are fixed values. For parameters, we have to define some starting values. So these are just default values, just to create the system. And as an option, you can put in initial conditions for your DE. You'll see later that you don't actually have to put it in here. You can actually change it later. So this is the stage where you can actually define how this component is going to look in MapleSim. And these are what we call acausal ports. So these are the ports that define the interface between this component and other components that you want to connect together. So these two ports are actually electrical pins. So this is the negative pin, this is the positive pin. And on each of those pins you have certain properties that come from those equations. And the way that you select those is you just choose, if you go click on the choose button, there's the drop down menu. Then what you have are all the all the states that were listed in those equations that we typed further up. They appear in this list. So you just select it from that. So for this pin we need two properties, voltage and current. So there's the positive and negative pins. For this port, this is a mechanical flange. So this is a rotating flange, and this requires an angle and a torque. And again, these just come from straight from those equations that you define above. There are many different domains in here, and in fact the next release there'll be even more. There are also, you can even create your own domains, create your own ports using a special language called Modelica, which is part of the product. So these define how your inputs and outputs are going to appear on this component. And then you click a button, and now we have my motor model, which I can now bring into the double, so this slider crank model I created earlier, and I can connect that motor to this joint, so I can drive this joint. So what I'm going to do now is just put some just go in here. Constant voltage. Rotate that. Together. So you can put a ground in here. I'll put a voltage in here. Okay, that's probably not enough. I should really put a gearbox in here let me just try 1,000 in here. Seminário. Something like that. Okay.
It's possible to invent that in a video in a presentation.
The visualization? Yeah. Yes.
Video in a presentation.
Yes. So you can generate an MPEG movie. Right. Sorry, I'll just put a ridiculous number in here because I'm just trying to get this thing to move. Okay. That's it. All right. There we go. So with this you can create many different visualizations of it, and yes, you can indeed create a movie of the system. In fact, I just go to this is actually the fun part of my job is creating movies from Maplestone. So we have things like belt drives, and then that we will move up to provide attention.
Do you know fun? Game
Yes,
fun.
yes,
It's
the
similar
PHUI.
to fun.
Yeah,
No?
but with equations.
So,
We
you have a nice equation and make
yeah. This is actually a demonstration for a company that's building a model flying bird. This is, and this was one of my favorite ones because sometimes when things go right, it's really boring, but when things go wrong, it's great. And this one just shows we need for the visualizations we can attach. Actually, let me stop this now.
Isso aí é um fã começar pra gente grande.
No, let's keep this going. So we can attach CAD components to those multi-body things and build up really nice looking visualizations of the models in this way.
Se um gráfico de Fábio gostaria de estar vivo.
And this is these CAD components that we use. We just pick up from there's a wonderful Google site called 3D Warehouse that is using a tool called Google SketchUp, which is you can get a free version of it. And there are some plugins that allow you to produce STLs, which is the file format that we produce here, or it's a standard format that comes with CAD tools.
Sir, I mean, does Maple, know, or does Maple, has Maple already made an account of the possible impact of these techniques for robotics, for example, people who are trying to work with robots? And so this may be extremely helpful.
Absolutely, yeah. I would say we certainly have many robotics companies that are using the products. Interestingly, not in the robotics that we think of as robot arms, but
Yes.
on autonomous machines, autonomous rovers. So there's a lot of work going on for unmanned planetary exploration. So in fact, let me close this. Let me just open up my presentation here. This is actually one of the. This is the Curiosity lander being developed by NASA at the Jet Propulsion Laboratory. This is an interesting one because they just recently acquired a major license, about 50 licenses, which is pretty big for us. The benchmark for this was to model the tethering system between the rover and the lander So in the past, the lander has been an integral part of, or the rover has been an integral part of the lander, and it hits the ground, and sometimes it will actually not break. So obviously they want to have more robust ways of dealing with that. So what this does is, as the lander is coming in, it actually lowers the explorer onto the Earth, onto the surface before this actually lands. When they developed this using MATLAB, it took them about 2 years to develop this. During an afternoon of training, in an hour, we had the basic components put together. Yeah, okay, I would say not everything that was done in the 2 years, but certainly to be able to visualize this thing and see it working and get the true physical behavior. It's a massive impact on these guys. So I wanted to spend just, how long have I got, by the way? Till 6? Yes.
It's a question. This maple or something like that works with the reverse problem. For example, you have some fontaine and you need to use a scattering pattern, and you can reconstruct, for example, the object which scattered the light.
Ooh.
I'm asking about that because, for example, here we have nanoscience laboratory,
Yes, yeah.
and they make optolithography. And one of the huge problems is that they have a mask here, and you have light for making the lithography. And the problem is that you have diffraction, and the figure you have after making the lithography is not 100% the one you would like to do, you know. So it would be very interesting if you can calculate before constructing your mask the diffraction pattern, the interference pattern, and then you construct already correcting it.
Yes, yeah. Well, okay, we have no magic function to do that, but it certainly has the potential to do that,
Yeah, for example, in Europe, in France, they make the mask for us.
Yeah.
They do it, for IBM does it too, but not using a program like that.
No.
You know, they program their own ways, and so it would be very interesting if you could develop something for
certainly
like that.
I mean, we have people, we have optical companies using maple syrup.
Yeah.
Unfortunately, they won't tell us what they're doing with it. So, this is one of the big problems we have with some of our customers, is that unless we sign an NDA or a non-disclosure agreement, we don't actually get to know what they're doing. Certainly, it has the potential of being able to develop your own solution for doing that.
For gas and oil, for example, it would be very interesting.
Yeah. I only have one example which might be close to, or distantly related to that, and that is we have some examples where we're using our multi-body components to do inverse kinematics. And what we mean by that is with a robot arm, for example, you have a motor here, you have a motor here, you have a motor here. You want the end effects to go from here to there. What do the motors do to give you that most efficiently? And that we're using symbolic techniques to do the inverse kinematics of those, so you can actually get a full analytical solution. It's not just a numeric solution. You actually get an expression for what those angles should be at each time step. I can imagine that something similar could be done with the problem you just described.
Okay.
But that's the best answer I can give you for now.
Okay.
If anybody wants, if we want to explore this further, we'd be happy to talk with your colleague and see if we can actually investigate some way of doing it. Renato can help.
Então, por isso, this was in Pasadena, no?
Yeah.
And Microsoft support them, including one engineer. So that they would CPPF here.
But they paid for it. Okay, I spent a little bit of time, because we are an engineering group rather than a physics group, just to talk a little bit about some of the more sophisticated modelling that we've done, and that's in the domain of battery modelling.
Just for you understand, these people here, they enjoy very much electromagnetism.
Okay, so this could be this is actually the project that was done by one of my colleagues, Sam Dow. So he's much more of an expert as I am in this, so I can only sort of just talk through what we did here and then give you some sense of how it was implemented in Maple Sim. So typically when you're for most kinds of applications, when you're modelling a battery, you're typically using an equivalent circuit model for doing this. This is a very simplified representation. Typically requires empirical data to do that. What Sam did was actually to focus on modelling the physics, actually modelling the ion transfer in the various chemistries for different batteries. And these are actually the results that he got from his physics-based models. So this is kind of the state of the union, the state of play at the moment. So experimental models using equivalent circuits, and what we wanted to achieve was to produce a chemistry-based model based on the ion transfer in the system. So these are the equations that we needed to resolve, and sort of done this. Yeah, okay. I think what it is. Now we jump to Maple Sim, and he's using Galerkin techniques to produce the battery model. And this is one example in here, as a custom component. So this is a nickel metal hydride cell, and really, the mathematics pretty much is the same for whatever chemistry you're using. It's really just down to the parameters that are being used. So these are the final ODEs that were developed or derived by using this Galerkin technique to take the PDEs and get them down into an analytical form that could then be used in Maple Sim. So once we have these equations, we just did what I showed you before. For my simple DC motor, we just type these equations in, and these are the parameters for the various for different chemistries. And then here's my components. So we'll move a little bit further. So here we have the electrical components, positive, so electrical terminals, if you like, positive and negative pins. And this is just a computation of the state of charge for the battery. And then this was put into, in this particular case, this is a wind generator that has control systems for feathering the propeller blades to control the amount of energy that's going into the battery. We have a rectification stage that converts the AC current that's coming in and turns into DC, which we can then use to charge the battery. Okay, I should run this because it takes a little while to run. Now, the main reason for the battery there is not just for energy storage. It's that if you want to plug this into the main supply, then you have to reconstruct the main signal, the voltage signal, to comply with the grid that you're going into. So it's 60 hertz or 50 hertz or 120 volts or 420 volts or whatever the grid requires. And then what we have at the end here is just some loading conditions that we were experimenting with.
Question?
Yeah.
The applications in molecular dynamics, the interaction
Good question. I don't know of any, but I don't know of anybody actually doing that, but I can imagine you could. It's, you know, you're just modeling hard, assuming that Newtonian models. I don't have any examples now. Yeah, I'm not aware of any examples. But I can imagine, you know, as long as you know the Newtonian models, then you can just create it in Ableton. Yeah.
Uma coisa que se chama Maple Application Center. Lá eles procuram colocar muitas aplicações que acontecem em volta do mundo. É Maple.
I don't think we have anything. I don't think we actually have any molecular models.
Lá eles disponibilizam. Tem companhias que não disponibilizam, entende? Essa questão. Isso aí tem uma história também. O cara lá faz ótica não vai disponibilizar. Quebrou a cabeça. Né? E desde aqui tem muita coisa. Então,
Yeah. But you can check. But I just can't remember seeing anything. Anyway, it's, you know, if you can model it with springs and dampers, and you can do it that way. But any other way of doing it, you'd have to specifically define what the forces are. We just don't have anything built in for doing that. So just to finish off this presentation, the more exciting thing is that you can produce a movie of this thing as it's doing its job. So, just to wrap up. Oh yeah, just talk a little bit about the code generation. So I haven't really dwelled on this because I don't think, unless there's anybody particularly interested in the code generation, perhaps we can talk later. But everything I have done, I've shown you here, you can turn into C code, and it's very fast C code. We've done some major benchmarks on this, and we've been able to demonstrate that we are, you know, an order of magnitude, sometimes more faster than our competitors. As I mentioned, this has two benefits. One is if you're running a simulation, then typically the simulation has to work at a fixed step, and typically it's 1 microsecond fixed step. So that gives you a hard stop. This thing has to work inside, 1 millisecond, was it? Must work within 1 millisecond, 1,000 times a second. However, you've always got some overhead in here that the system needs. Sometimes it can be 10 microseconds, sometimes 20 microseconds. But that gives you a hard budget of time in which you need to be able to execute your models. And the particular project we're working on with the competitors, yes, would work within 1 millisecond, but would not work within the budget because of the IOs. So we needed to have something that was going to address that problem. And our particular model ran at a tenth, a fraction of it. And this really validates our approach, the symbolic approach to defining these models and generating the code. But what is probably more of interest to you guys is the fact that this code can be used for very fast executions. And by the way, I didn't mention it, but you can run these compiled models actually within Maple, and you can run them on parallel processors. So you can carve up the processor with several processors and get much more performance out of the system. So just to wrap up my presentation, you know, I think I'm hoping that you see that we certainly among our customers, we're seeing a great. What's driving a lot of this work is the drive towards greater efficiency in the design, specifically in energy efficiency. So physical modeling is becoming increasingly important for doing this, and also increasingly complex. There's a lot more detail that you have to get into the models. You can't always get away with using an average value model. You have to get into the detail. And that's an important factor for the systems design, the testing, and the integration with the rest of the product. Symbolic technology is a new technology, but it's a proven technology. It's just starting. We are driving this, but it does significantly help to improve the fidelity of the model without sacrificing performance, and make Sims the ideal tool for doing that. And I'm hoping that you can see from here that it's an ideal tool for developing those high fidelity models for complex systems to help you guys to achieve your design goals. So with that, I'd like to thank you, and if you have any questions.
We stay here in Brazil until Rio de Janeiro till which day?
Sorry, I'm here.
Yes, just for today.
No, I'm here until Friday.
Until Friday.
Yeah,
okay,
but
because if some of the students want maybe to ask you a couple of questions and we get together, people will be available here.
Yes.
Eu estou passando uma lista aqui de deixar e-mails,
ok.
e daí a gente contata cada um por e-mail.
Renato is always here.
Okay, yes, always here, especially in this class.
These people here, the obligation is to develop new theories. Let's say, if the gravity is 1 over r squared, not to be 1 over r5. So they are always this is the idea. But now these institutes, they want to unify science and innovation. So let's say, giving one new theoretical model to create some innovation.
Yeah.
Can be in chemistry, can be in,
Yes.
doesn't matter what subject.
Absolutely. Yeah.
And we'd like to listen from you, your general idea. How, because you also belong to one generation that it was very hard to do innovation
Yeah.
from science.
Yeah.
And what is the facilities that we are having now? Because we don't know clearly this kind, and we'd like to listen from you.
Oh.
Facilities to make this bridge between science and innovation. With maple syrup.
Okay. Well, I'm not quite sure I understand the question. I mean, we
Let's say you have a theory, you have
Yeah.
some equations
Yeah.
for something,
Yeah.
and then you need to create innovation for that equation.
Yes. Okay.
And how maple syrup can be helpful to save the time and
Well,
money.
We put the innovation directly connected to basic science, or is there technology in science you have to first of all?
Yeah, basic science and innovation. I would like,
After technology, you go to innovation.
yeah, from the basic science, how to make bridge it from innovation. Let's say, in the end you make the technology corresponding to that innovation. But let's say, your basic science not be alone. I just discovered the electron. I have to do something with this electron. Okay?
So I mean, my only comment is that, first of all, we're not in the business of making sort of fundamental research,
Yes.
turn it into innovation. We're in the business of developing tools to help you
Yeah.
do that.
Yeah.
That's really our fundamental motivation for developing these tools. Certainly, the kind of mechanisms that are in place, those are defined by our customers. And you go to JPL, you go to Bell Labs or Goossens, and they're using these tools as a way of being able to facilitate that whole process. So I don't know if that answers your question. I'm not sure if I fully understood your question, but we just see our tools as a way of being able to facilitate that whole process. We're not there to be able to define that process or to create that process.
But let me make easier Dory's question.
Yes.
Because instead of starting off a fundamental or basic science, it seems to me that for you people at Maple, it's better you have some technology, and once you have this technology, you can go to innovation, or because if we start from the basic sides to go to innovation, I mean, maybe this is not your business. Your business maybe is to have technology, and with that technology, you know the equations which govern those mechanisms, and from that you can, let us say, innovate. Is it so?
Well, absolutely, yes. Yeah, I mean, we have within Maple some very innovative technology techniques, and but there are techniques that really maybe only a small number of people are actually going to use, or maybe even a smaller number actually understanding or actually using it. It's just when they present a problem, Maple then applies those techniques to it, but they don't know that those techniques are being applied. So we're always looking at ways of being able to implement those kinds of solves and algorithms. Maple Sim itself is pretty groundbreaking in the solving of differential algebraic equations, DAEs. We had to be. The whole nature of the types of models we're creating. We're constantly introducing algebraic constraints into the system. And we're producing very high index DAEs. So under the hood, we have taken innovations from many different research institutes and implemented them as part of our solvers. So certainly in that kind of area, we will always facilitate that kind of process and innovation.
But I would ask, they have here one department for nanotechnology. In which sense do you think that Maple Sim can be helpful for nanotechnology?
I'm not entirely sure what I mean, certainly anything that's involved in the mechanics, or if you're looking at non-Newtonian physics within those components, well, okay, what we have built into the product assumes Newtonian physics, but you can switch all that off and put in your own force equations or whatever is required to implement those things. So I would say what we provide is a platform that allows people to implement those kinds of innovations. We just don't have a nanotechnology package as part of the. But if you guys are thinking of it,
yes.
we're putting it in.
That's the challenge.
Yeah, I mean, I'd say that the smallest we go is medicine in terms of the kinds of applications that we're working on there. But certainly, if there are some common techniques that need to be implemented in a modeling tool, we'd like to hear from you.
Eu vou só resumir, vou colocar só você, como hoje foi o lançamento do Blink 16, quero colocar para vocês que houve um grande desenvolvimento do Blink 16 para a física. Então, ele tem pacotes de geometria diferencial, tem pacote só de física, certo? Tem pacote para teoria de grupo, enfim, onde eu vou deixar com a professora Lael aí isso aqui falando sobre as novidades do Blink 16. De quem quiser procura ele na sala dele, certo? Então, quer dizer, o que eu entendo, e eu não entendo muito, o que eu entendo é o seguinte, vamos dizer, você hoje em dia escreve uma lagrangiana tensorialmente, o Maple tem um pacote de tensores, você resolve todas as equações de movimento, tudo, vai para equações diferenciais, o Maple é o melhor software para equação diferencial parcial não linear, então você pode resolver sistemas de equações algebricamente, numericamente. Depois ele tem sistemas dinâmicos, você pode ir para o sistema dinâmico e daí você pode entrar no meio possível para fazer inovação. Então a tua lagrangiana é a história da vaca, né? A vaca você corta daqui, dá um bife, do outro lado. Você pode ir pegando a tua lagrangiana e fazendo muita coisa com a lagrangiana. Tá? Então hoje em dia a indústria de softwares está permitindo que você no one like no mathematics skills. Então, sem saber matemática, sem saber nada assim, de matemática como matemático, você pode fazer muita coisa hoje em dia, sabe? Então, eu acho que a lagrangiana, que uma pessoa propõe, uma teoria propõe, ela pode ser muito desenvolvida em muitos pedaços. Né? Dá para abrir o portão ainda da Lagrangeira.
Oh, thank you, sir, so much.
Thank you.